Hi team, thanks for showing up for your learning. It is a Wild Math Wednesday, and we are going to be looking at this topic, families of quadratics. I give you the roots of a quadratic, and you're going to find its equation. So a family of quadratics, that just means that we have a group of parabolas or a group of quadratics that share common characteristics. In this case, we're going to see that they share roots. So here, one activity for you will be to pause the video and then go ahead and fully factor each of the following equations. Remember that you want to start with common factoring and then move into other forms of factoring. So as you can see, all of these, once you have them fully factored and you take out these a values, all those other values are equivalent besides these a values. And then that gives you quadratics that all share the same roots. In each case, 5, 0 and negative 2, 0 are going to be the roots of these quadratics. And so let's take a look at what these would look like if we were to graph them. Here are these four quadratics. They all have the same form, y is equal to a x minus r times x minus s. They all have this root here at negative 2 and this root at positive 5, but a variety of stretch factors. So this one here was the original one, just had a stretch factor of 1. Its vertex well down there. This one was the one with a negative stretch factor of 1/2. So we see that it's been flipped in the x-axis and it's been squashed a bit. This one it would be the also have a negative stretch factor, and this one also positive. So a variety of different ways of showing the same idea. Now, we're going to be using that idea of having the factored form here, where we can express a quadratic as a function of x such that a multiplied by x minus r times x minus s gives us a quadratic, gives us a parabola, where r and s are the roots. So if we want to determine the equations of a full family of quadratics, what we would write here is f of x is equal to a multiplied by x minus the first root, and there will be one of our roots, so x minus 4, and then x minus 2, the second root. And that creates a family of quadratics where a gives us the stretch factor, and there's an infinite number of those. And I can show you those in the Desmos here in the graphing calculator. So here we go. This is what we had written there. And a is this number that will change. This is an a of 1. And as we can see, it's a parabola that's unstretched. If I bring that down to a half, then we see it flattens out. And if a gets very large, it gets very stretchy and the vertex dives downwards. And as a is negative, it reflects in the x-axis and then goes in the other direction. So there's an infinite number of those that share those roots 2 and 4. And if we had another point, like let's say we were interested in this point 5, 6, let's say. So we have that point up there, and we want to know what's the quadratic that goes through that point. I could actually use this situation and say, well, I can stretch this quadratic, and there, that looks like it got it. When a is 2, that seems to bullseye that point right there. So the quadratic that goes through 5, 6 and has roots at 2 and 4 would be 2 multiplied by x minus 2 times x minus 4. So this is the idea that we're going to use to find quadratics. Now there's one situation that will come up a fair amount, and that's where we have radical roots. Roots where there is a rational component and a radical component. Like x of 1 is 3 plus the square root of 5 and 3 minus the square root of 5. Apologies that fell onto the next line there. And so let's create this one. In order to do that, just like when we have a simple number like 4 or 2, you're just going to plop that into your formula. So in this case, it's still going to be a function of x is equal to a multiplied by x minus, substitute into brackets here, 3 plus the square root of 5 multiplied by x minus 3 minus the square root of 5. And then you could say, well, we're done. Or you could simplify inside the brackets. So we're just going to distribute those negatives. A multiplied by x minus 3 minus root 5 multiplied by x minus 3 plus root 5. And then you might say, well, Mr. Jennings, it says sketch them. We should be able to graph this. And I don't know how to graph 3 minus root 5. Tell me what that is. Well, if you check on your calculator, what would root 5 be? Well, it's going to be bigger than root 4, and root 4 is just 2. So we expect that this number is bigger than 2 and smaller than 9 because, well, we could create this type of equation to show this, right? Where root 4, 4 is less than root 5 is less than root 9. So we know that it's between 2 and 3. So let's go ahead and approximate that. And if we did a decimal approximation, it works out to be about 2.2. So let's go ahead and do a decimal approximation of this function. We would have a multiplied by x minus 3 minus about 2.2. So that's about x minus 5.2. And then x minus 3 plus 2.2. So that'd be about x minus 0.8. Okay. These expressions give us the roots, those factors, sorry. And so the roots would be at 0.8 or thereabouts, and at 5 and a bit, or about there. Okay. And then quadratics, they're going to have their vertex right smack dab in the middle of the roots. Notice that these numbers are giving us the axis of symmetry. That's the line that's that the parabolas are symmetrical around. So maybe one of them has a vertex down there, and it would look something like this. And maybe another one has a vertex well up here, a little more stretched and opening downwards. And it might, missed that one. And, bullseyed it. There you go. So you might have quadratics that look like that. So how are we going to do that to find equations of specific quadratics? That's really what kinds of questions I'm going to be asking you about on the tests and things. So in this case, we're going to start by creating our family of quadratics with the two roots, x is equal to 2 and x is equal to minus 3. So I know that I'm going to have some function at x is equal to a multiplied by x minus 2 multiplied by x minus 3. So that's just x plus 3. And then I'm also told this extra piece of information, that the parabola also goes through the point 0,3. So just to remind you, we had a family of parabolas here, and there were infinitely many, because there were infinitely many a values. But once I said I want it to go through another point, like the point 0.36, it was only the value a is 2 that would do that and bullseye that point. So when we're given that third point, we're going to go from having a family of an infinite number of functions to one specific function. And to do that, we're just going to substitute that in for x and y. So let's do that. So the function is equal to 3 when we have a multiplied by 0 minus 2 and 0 plus 3. Okay. Okay. So all I've done there is substituted in for x, the value 0, and y, the value 3. So 3 is equal to a multiplied by 0 minus 2. Well, that's negative 2. And 0 plus 3, that's 3. So together, that's negative 2 times positive 3. So that's negative 6. 3 is equal to negative 6a. And then, to solve that, we're going to divide both sides by negative 6. And that gives us the value that a is equal to negative 1/2. So, therefore, the function f of x is equal to, just take this a value and substitute it here into the function that you created, negative 1 over 2, x minus 2, multiplied by x plus 3 is the function that that has roots of x is equal to 2 and x is equal to minus 3 and passes through the point 0, 3. You could check your work by substituting this point in and making sure that when you put in 0 here, you indeed get 3 as the output, and inputting these two x values and making sure you get 0 as the output. You could also just dump it all into decimals. So let's do that. So we're going to remove these and just check our work here. -1/2 x minus 2 multiplied by x plus 3 and the bracket. So this has roots at -3, 0, 2, and passes through the point 0.03. So that one fit the bill, so we did our work correctly. Now we could do this in specific situations to model things that we have in our world. For example, if we have this highway overpass here and its shape can be modeled by a parabola, and we have put on a set of axes here which very conveniently locate one edge of the road at the point 0, 0 and the other edge at 10, 0. Let's take a look at how we can use this idea. We're also told that the height of the overpass, 2 meters from the edge of the highway, is 7 meters tall. So let's put that point on as well. That's the third point that we're going to need to find the specific shape of this highway overpass. So here is the 2 meters from the edge of the road. It's going to be above that point, and it's 7 meters tall, that high. So that's about that point right there. And we're looking for the parabola that's then going to model this shape, go through that point, have a vertex up there at the top of the road, come on down, and be going through that point 10 there. All right, so let's see how we're going to do this. We're going to start by using the factored form. So we're going to have f of x is equal to an unknown value a, the stretch factor, multiplied by x minus 10 minus the first root, and then the second root is x minus 0. So there you go, that's x minus 0. And now let's plug in our point. This point was the point 2, 7, and let's plug it in to find the value of a. So we would say the output of the function is 7 when x is 2. So a multiplied by 2 minus 10 times 2. And then let's evaluate. So 7 is equal to a multiplied by -8 times 2, -16. And now, to solve that type of equation, of course, we're going to divide both sides by -16. These 16s will cancel, giving us the a value, which is -7/16 is equal to a. So we're going to say, therefore, the equation that models the bridge is f of x is equal to -7/16 x times x minus 10. And there you have it. So if you have any questions with the practice problems for this one, you can feel free to hit me up by email or come find me at lunch. And otherwise, thanks very much for showing up for your learning. And I look forward to seeing you when you're back in class. Bye for now, everyone.